Alright everyone, welcome back to the final part of lecture number 10. In the beginning of lecture number 9 and lecture number 8, when we first began talking about derivatives, we saw an example where we took the position of an object and we found the speed at which the instantaneous rate of change at which the object moved. So we call that the speed. And we got that from taking the derivative. So we saw that when we took the derivative, we got the speed of the object as it moved in time. I believe we used an example where a ball was being dropped. Now, much like we can use the derivative to find the speed, which we also call the instantaneous rate of change of an object. We can also obtain the acceleration of an object by taking the derivatives. In particular, when I say speed, I mean velocity here. Let me just use the actual word velocity. Velocity, speed. I use that interchangeably. So in particular, by taking the derivative of the velocity function. That's why I renamed it again. Because most books will use velocity function. It's okay to call it speed though. Okay, so what do we mean by this? When we began talking about derivatives, we saw a position function which we call s of t. And this is our position function. So this is a position function. We saw that when we took the derivative of s of t, if we did s prime of t, that was equal to the velocity function v of t. So this is equal to the velocity function. Notice that we got a function after we took the derivative. Well, if we take the derivative again, this time of the velocity function, it will be like taking the derivative of the position function twice. So I'm gonna write it with two apostrophes, and that's what we call the acceleration function a of t. This is the acceleration function. So if you take the derivative once of a position function, you get the velocity of the object, and if you take the derivative again, then you get the acceleration function. This function a of t we call the second derivative. So this second function a of t is called the second derivative. Okay? It is denoted by, as I wrote, s double prime. We read that as s double prime t. Now, the second derivative is an example of a higher order derivative. So the second derivative is an example of what we call a higher order derivative. So, you know, there are functions for which you can define any positive order. For example, you could have a third derivative from a second derivative, you could have a fourth derivative, and so on. So, you know, you could have a first order derivative. So first order or first derivative will be y prime, and the second derivative will be y double prime. And you could have a third derivative, y triple prime. And you could have a fourth derivative, y quadruple prime. So people write it like this. You may also see it as, y to the fourth in Roman numerals. And you could go, until the nth derivative. You could have 10 derivatives, 1,000 derivatives, and this will be denoted by simply y to some n up here. There's other ways of expressing this. So if you were using the f notation, it will be f prime of x, f double prime of x, f triple prime of x, f to the fourth of x. You can also use a number here. I've seen it with Roman numerals or numbers, and f n of x. You could see it with the dy dx symbol as well. So this will be dy dx. This will be d to the 2y over d to the 2x, and so on. Just too close to that. So this will be d to the 3y, d to the 3x, and this denotes that you're taking more than one order derivative. So y up here. This is a y, this is an x. They look almost identical. The way that I write it, looks almost identical. In any case, let's do one example of finding the speed or the acceleration of an object. Now, we all know that the moon has no atmosphere. So, because the moon has no atmosphere, a falling object on the moon encounters no air resistance. If you ever have taken your hand outside of a moving vehicle, and just extend your hand out and your palm flat, then you will see exactly what I mean by air resistance. Well, it turns out that in the year 1971, an astronaut by the name of David Scott, he demonstrated that a feather and a hammer fall at the same rate on the moon. A feather and a hammer fall at the same rate on the moon. Now, the position function for each object of the hammer and the feather is given by the following. This position function for the falling objects are the following. S of t, remember this is a position function, so we call it S of t. S of t equals negative 0.81 t squared plus 2. And S of t, it was the height in meters, and t is the time in seconds. So S of t is the height in meters, and t is time in seconds. Now, to find the acceleration, we just have to find the derivative of this position function twice. So if we wanted to simply find the acceleration of these two objects, well, we have this as their position function, so we just have to take this derivative twice. So if you take the derivative, the first derivative of s, you have 2 times 0.81 plus 2. Now 2 times 0.81 is going to be equal to minus 1.62. Yeah, 16 and then 2. Yeah, so minus 1.62. And then the derivative of 2 is just 0. And we have a t here, because we had a t squared. So it's going to be negative 1.62t. Now, to find the acceleration, we take the derivative twice, and that's going to be minus 1.62. So the acceleration due to gravity on the moon, acceleration due to gravity on the moon is negative 1.62 meters per second. Okay, now let me just put this into perspective, because to you this number may not mean anything. I forgot who figured this out, but there's a formula for the gravitational force for the Earth, and basically, to make a long story short, the acceleration on Earth due to gravity is equal to minus 9.8 meters per second. So it makes sense that because there's no air resistance, this number is much smaller on the moon. That's why you see people floating, because you do not accelerate down as fast as you do on the Earth. On the Earth, you accelerate down much faster than in the moon. In any case, this is just one example of how you would find the velocity of a particle. Sometimes you may have a variable be left over, and if that's the case, you're also given a point, because usually you'll be asked to find the acceleration at that particular point, and that's perfectly fine. That is the end for lecture 10. Thank you for your attendance, attention, and participation.